All right, so yeah, welcome back to this channel. In the last video, you have successfully learned. Hopefully, you have successfully learned how to develop a image classifier model in TensorFlow. We have also looked at a pretty interesting dataset, Williams image classification dataset. So in this video, I want to introduce you to some little more sophisticated architectures. Actually, one architecture in this video will cover ResNet. So ResNet is an architecture. I'll cover the theory and why we should use it, why we will use it. So let's start off by discussing about a problem in computer vision, right? So we have already learned about you have already learned about CNNs. I have explained about CNNs in the one of the past videos. So in now I will cover a limitation of CNN. So why sometimes it can be it can cause a problem. This problem is called vanishing gradient. I'll talk about the problem, and then after that we'll figure out that the solution is ResNet, right? So using ResNet we could solve the problem. So the problem goes like this. So in a CNN we have many layers, right? So let's say we have many layers. Let's say these are all kernels. So these are all CNN layers, not a feed for a neural network, right? These are CNNs, let's say. So each layer will have, let's say, n number of neurons, and then we'll flatten out this, and then it will goes into a neural network. I'll just nn, right? So let's say we have this simple architecture of some CNN layers, right? And then we can just flatten and put it into neural network. So the one thing that I want you to remember or keep in your mind, is that in a CNN, right? So the in most commonly in the early layers, right? Most commonly we have many neurons in the early layers. So we have, let's say let's say 50 100 neurons or kernels in the first layer, and then we'll keep on decreasing until here. So the early layers will have many neurons, and as the input is like we'll get a huge input, right? So what will happen is this early each kernel, so each kernel or each neuron, right? So or each kernel will track a feature which is pretty low level. So let's say I have my face image going through a CNN. The early layers will detect very small features such as edges and colors, and very pretty small features, right? So we have many neurons, hence each neuron will track very minimalistic and little features that can make difference. For example, let's say if you are talking about problems such as skin cancer detection and all that, you just input the computer an image of a mole, let's say a scratch or something, and then the computer has to figure out if the scratch is of a um, skin cancer or not, right? So if you just input the image like that, the early layers, right? So we have the layers coming from the first, right? So as the image will pass through the CNN, the early layers will track very small features, very small edges, very small like very minimalistic features, as we have more neurons. And then as we progress through the CNN, as we progress, these features will be combined to be used to to track another features, right? So we have edges and all that little features are detected in the early layers, and as we progress, these features will be combined to track a little more larger features, right? That is what going to happen. And as we progress, these features are going to be smaller and smaller, and hence we'll get a feature representation. So the layers comes afterwards. So the layer that is that is closer to the neural network will have higher importance than the layer of these early layers, right? So this layer will have lesser importance than of this layer. So this layer will have higher importance than this layer, right? So that is why that is a problem that that is a problem in CNNs. Whenever you have minimalistic features that can make a difference, for example in skin cancer, as I've just proposed, in skin cancer detection, there are minimalistic features, very small features that make the whole difference. So when you want these features to be as important as the features that are coming, that can be detected in the following layers. We we should use a network called ResNet. So that is a problem. This problem is called vanishing gradient. So the gradient or the importance given to this early layers vanishes, and then as we go through this CNN, this the importance given to this layer will just keep on reducing, and in mathematical terms that is called gradient. All right. So that is a problem, vanishing gradient descent. Ah, okay. So that is problem of vanishing gradient descent. Right. So we have to solve this problem. So that is the problem. That is the problem we should that is a problem in CNN, right? So how can we solve this problem? So so how can we solve this problem? Well, we have a so the solution is pretty simple. So you might have even guessed it now. So what is the solution is, we'll just take this gradient for example, and will just add it here. All right. So we will just take these outputs of this neuron, the earlier layers, and then we'll just add this output of this layers to the furthermost layer. Or to be more precise, uh, to be more precise to our implementation that we'll be doing, we'll have another layer which will have only, let's say, one CNN layer that will take the input parallel to this layer, the main layer also, and then we'll feed it to the here, feed it to the or add it to this final layer, and then and we'll do the same process. We'll flatten out and send that to a neural network. So that is a solution. So we'll just create a new layer which has, let's say, only one CNN layer, and then it will take the same input, and the features detected will be added to these final CNN layers. Hope you understand what is going on. I'll also link the research paper below. So this is the research paper. So this is the research paper. Make sure to read it. Very simple. If you don't understand, if you do understand, sorry. So if you do understand CNNs, then definitely you can understand this paper also. Deep residual learning, right? I think it is wrote by Microsoft Research. These gentlemen here have wrote this paper, or these people here wrote this paper, right? So that is a solution. We'll just create a new layer, and then we'll just have minimalistic neurons, and then we'll add it to this final CNN layers. Now let's implement it. So this is the code that we have written in the previous video for solving the previous problem. The problem is actually pretty simple. As we have only 20 images, it is very easy to get to 100% accuracy. But what we'll do here is, we'll use this network. We'll try to build this replicate this network, and see, like, we are not going to get any huge differences in performance. We're not going to get faster accuracy, because this problem is as really minimalistic, and the differences are pretty they are pretty obvious. There are this, I think, like, there are no smaller differences that can make a difference, right? So the features are pretty big, so we don't have to use a sophisticated model like ResNet. But let's this is just for learning purposes. For this lecture, I'm going to introduce you to a new style of model development in TensorFlow. This is called functional development, I think. Functional model development. So this is how you do it. You can just use variables to define layers, right? So you can just store these layers inside variables. So what I'm going to do is, I'm going to say, first I have to define the input layer. When you are building models in functional API, using functional API, I guess. So you can just say, right? You can just say, you can just say tf.keras.layers.input. You can just first create an input layer, and what is the shape? Shape is here. We have set the shape here, right? Inside this image data generator class, we have specified the target size, which is equal to 150 by 150, right? So the target size is 150 by 150, pixels. So I'll just say the input shape equal to 150 by 150 by 3 because we have three channels R, G, and B. And then we have the next layer X1, let's say. And then let's do the normal CNN conv 2D. Let's say we do something like 64, and then we have 3 by 3 kernel, and let's say we'll have the activation of ReLU. Right, so we have I here, and then let's define X2. So we'll have first we'll have um, these two layers. It's a 128 by 1, let's say. In order to match up the shapes, we'll put 1 by 1 filter here, and then we'll say activation function to be ReLU. And let's put X1 here, and then when we are building X3, we'll build a new, like, so as you can see here, I'll just define the syntax first. So he has the syntax to build a layer. So we have X1 layer here. So we can just define the layer here, right? As a function, we can call it. And after that, we have to specify the input to this function in this brackets, right? So we should specify another set of brackets, and we should input this. We should type in the input to this function. So what will be the input to this layer, to be more precise? So we have I to be the input of this first layer, and after we have computed this X1, we'll define the X2 layer, and the input of this X2 layer is X1, right? So as in CNN, the output of one layer is the input of the other layer. So therefore, we have X1 to be the input of X2. And then now let's create the parallel layer with only one CNN layer. And so I'm not going to go build a deeper model because we don't need it. Right, so we have a very pretty simple problem here we are solving. And then what should be the number of kernels? It should be 128. Why should it be 128? Well, because as we want to add this both X2 and X3, let's say as we want to add both X2 and X3, what should we do is we should make sure that the shape of X2 is equal to the shape of X3. And then what is you can just make it to be 3 by 3. Well, because the output of these two layers combined, so X1 output is going to get to X2, right? So we can match these outputs only by using these parameters. And then we could have an activation layer, right? And then here to X3, the input is I. As I have told you, we are going to build a parallel layer. So this is one set of layers, X1 and X2, and this is another parallel layer, X3. And then what we are going to do is we are going to add X2 and X3, right? So I can just say X4 equal tf.kras.layers.add. So there is another function called add, and then inside this add, I can specify, right? Not inside the add, we have to create another set of parentheses. Inside that, we can specify a list of the layers that we want to add. So I can just say X1 or sorry X2 and X3. Understood? And then we can just continue. We can just do the flatten thing. Just flatten the outputs. X4, and we can just get the X6, get dense layer. So how many neurons can we have? I don't know, 256. Let's have 256. We'll use ReLU activation function again. Then we'll say X5. Then final layer X7 equals. Should we add a dropout layer? I don't think. Right? We'll just say we'll add the final layer 5 activation equals softmax and X6. And then yeah, we have defined layers, right? So to create the final model, just have this final variable model equal tf.kras.model, and then you should specify the input and output. I can just say inputs equal to I, and outputs equals I have to specify the last layer. So I can just specify X7. That's it. The model is created. I'll just run it. Hopefully it runs. Yeah, the model is I have the model now. I'll just compile the model now. I'll just make sure the I will just specify the optimizer and the loss functions. I think it ran. I'll just run it. Yeah, it ran. Now let's train the model. It might take some time, a little more time relative to the time it took for the last video. I'll just run it. I'll pause the video for now, and I will see you after training. All right. Yeah, the training is over. Okay. So like there is no difference in performance, the previous model also hit 100% accuracy. We also hit 100% accuracy with this model also, but we can be able to see the difference when we are creating or training with we are when we are solving a more complex problem such as skin cancer detection and all that. Like we can see the differences then. Now let's see how we can develop a more sophisticated ResNet using TensorFlow, right? So we have TensorFlow that can provide us with a a pre-built function that we can use to create our own ResNet. So we have this. So what we should do is we can just create another class, right? Or we can just call a class. It goes like this. We can just say ResNet equals tf dot keras dot applications dot I think it is resnet 50. I'll select that, and we can just say include top. So include top here means should we include the so resnet is it's actually a complete model in which we also have the CNN layers and also the uh, feed forward layer. So if you don't want the feed forward layers, you can just say false, because we have our own feed forward layer. So we can just say include top equals false, and we should specify another parameter called weights equals image net. I'll explain what this is. So here, so like ImageNet is a data set. It is an online image data set. It contains of 100 like 1,000 classes of data. So we have data of belonging to 1,000 classes, right, or 1,000 types, and then we have all this data. And so what we mean by weights equal ImageNet is we are like when the model ResNet is trained on ImageNet, we have all the weights, right? We're going to take the weights or the pre-trained parameters, and we can just stop the training. So that this idea is called transfer learning. So we have already trained the model ResNet on a more bigger data set, which is called ImageNet data set. And what I'm going to do is I'm going to use these weights as like it's already pre-trained, right? I'll just stop training these weights, and I can just change this change this weights of this feed forward neural network. So I'll just input that, and what we'll have input shape. What is input shape? It is equal to 150 by 150 by 3. I'll do that. Then finally I can just use it. I can just say here x1, let's say x1 equals resonate, and I'll say I and I'll put x1. All right, understand? I'll run it. Hopefully it works. I have an error. What is the error? The weights should be either none, ImageNet, or ImageNet. Okay, I should actually it's spelling error. I can just actually just put it in like small letters. I'll run it again. Yeah, it worked. Now let me just compile the model. Again, it is not going to make any difference. I'm just doing this just to make sure that you have an idea of how to develop this ResNet, right? So, and we'll just have sometimes. So here, right? Wait a minute. I will just have to do another step, right? So yeah, the memory is hovering, just for education purposes. So what you should do is, if you want to freeze the weights, as I've told you in just a moment, like before just a moment, you know the main idea of transfer learning, of already using pre-trained weights, in this case of already using the pre-trained weights on ImageNet dataset. What should we do is we can just freeze the parameters, or we can just freeze the weights, such that we don't have to update these weights again and again while in the training. So I'll just say for layer in resnot dot layers, I'm gonna say layers dot trainable equals false. So by just including this couple lines, what I'm doing here is I'm just stopping the training. So I'm not going to update these parameters of the ResNet during optimization. So that is the meaning of this. I'm not going to run it. I think the memory is finished. So thank you for watching, and see you in the next video. And goodbye.